The parallel postulate, or more properly Euclid's fifth postulate, was a mathematical problem child for over 2,000 years and was a great example of what happens when you don't take Einstein's advice. So it all started around 300 BC with Euclid's Elements, the classic text on plain geometry. As math books often do, it starts off with a set of assumptions or postulates. The first four are just straightforward descriptions of some basic physical relationships that anyone with a pencil, a piece of paper, and a little free time would have no trouble convincing themselves of. The fifth one, on the other hand, is a mathematical dumpster fire. It's long, it's complicated, it's got multiple lines, it's got multiple angles. It's way busier than any of the other four. Now, to be precise, over generations of playing around with these things, people came up with a number of different equivalent ways of saying that fifth postulate, one of which is what today we call the parallel postulate. So here's where this excess of complexity becomes a problem. For 2,000 years, people struggled with the question, is that fifth postulate really a postulate? Is it really something we have to assume? Or could we actually derive that fifth postulate from the four that came before it? Now, at this point, it would be perfectly reasonable to look at this and think, wow, that is so inside baseball. Right? The kind of thing mathematicians argue about at conferences while engineers are off using it to build bridges that don't fall down. So here's why this is still relevant, and it says something important about mathematical and scientific research. Sometimes the struggle to show something, even if it ultimately fails, can still come up with useful results. For example, in the 11th century, a mathematician named Ibn al-Haytham tried to prove the fifth postulate from the previous four, and failed, but in the course of his research introduced the ideas of movement and transformation into geometry. So over the next several centuries, moving forward from al-Haytham's time, multiple mathematicians, including the poet and philosopher Omar Khayyam, would brush up against the idea that interesting things start to happen if you don't assume the parallel postulate is true. But it wasn't until the 19th century that János Bolyai in Hungary and Nikolai Lobachevsky in Russia realized that removing the parallel postulate entirely left you with two logically consistent and completely new forms of geometry. Now, Lobachevsky famously considered his new geometry really to be a bit of a toy, but further proving my point, a century after he developed it, Einstein would discover that so-called hyperbolic geometry and use it as a part of the development of his theory of relativity. So, not to leave you in suspense, in 1868, it was shortly after the time of Bolyai and Lobachevsky, another mathematician named Eugenio Beltrami proved that the fifth postulate is, in fact, independent of the first four, finally putting the question to rest. But the key point that I would like you to take away from this, and that I think you can take to your students if you're teaching this material, is that the struggle can be just as important as the solution. That it's possible to get insights that are new and interesting and valuable, even if they aren't necessarily the ones you started off looking for.